I'm Misha Fomytskyi from Vola Dynamics. Today we're going to talk about theta. We're going to discuss theta not just because this is my favorite Greek, but also because over the last month, at least 3 different clients asked questions about it. Right now we have almost 50 clients in different geographic zones. We have clients in high frequency, hedge funds and major banks. They're some of the most sophisticated financial institutions and most recognized financial institutions. And there are literally hundreds and hundreds of quants and traders using our infrastructure. So I think it would be useful to explain how we define Greeks, why we have how our definition of theta is different from the textbook definition of theta, why we have several thetas, and what's the motivation for this, and how this can be used. Let's start with the textbook definition of theta. So everybody knows that theta is the partial derivative of the option price with respect to time. In other words, it tells you how much the option price changes when your time changes by 1 day. That's how it's commonly defined. So what we would like to discuss is why traders care about this number, and what is the time with respect to which we calculate the derivative, and also what stays the same when the time moves. These are not trivial questions, and they require some clarification. So let's go and discuss this. Before going into technical discussions, let's first talk about why theta is important, why I consider it the most important Greek in derivatives trading, and why people use it. First of all, people buy options as financial insurance on their portfolios. Theta tells you the daily cost of this insurance, essentially the insurance premium you're paying. Same thing when people buy options to gain leverage. That's your daily cost of leverage. When a trader manages derivative risk of the portfolio, the major concern is exposure to convexity, to tail risk. Although you cannot reduce the risk of the derivatives portfolio to just one number, but theta would be the best candidate for such a number. First of all, it's expressed in units of dollars per day, so you can aggregate it across different underliers and expiries. And also, in the end, it's kind of telling you whether you are paying for financial insurance or you're selling it. Although this is not a perfect risk measure, but if you were to use one risk measure, that would be the one. As I mentioned before, theta is defined as a derivative with respect to time. But which time? It turns out that in derivatives modeling, you may have more than one time also. So if you look at the Black-Scholes equation or Black-Scholes PD or SDE, you will always have time either multiplying by some rate or multiplied by volatility squared. In other words, time measures either the rate at which interest is accrued or the rate at which variance accrues. And when you model option prices, it is convenient to separate them. Why this is important, and why textbook derivative doesn't really make sense in practice. So, for example, the interest accrues usually once a day. So infinitesimal derivative with respect to time doesn't make any sense because the interest is not paid intraday. Also, when you are calculating the amount of interest paid from one day to the next, you need to take into account settlement of sets. That's a big separate topic of how to do this. When it comes to volatility modeling, we know that variance accrues faster during the day and slower when the market is closed. There are also some bursts of variance, burst of realized variance when there are any economic announcements or earnings announcements. For this reason, People usually model this by defining custom volatility time that absorbs these fluctuations of the rate at which variance accrues into volatility time. In Vola Dynamics library, therefore, we have two different times. One is time v, the rate at which variance accrues, and time c, the rate at which interest accrues. Now that we defined volatility time and rate time, you know how to use them. If you want to calculate the amount of interest paid or over some period of time, you multiply time c by the interest rate. And if you want to know the total variance, you multiply volatility squared by volatility time, or time v. Then it is convenient to define two different thetas. Define theta v as the derivative with respect to volatility time, and define theta c as the derivative with respect to rate. Why is this important? Because those two Greeks, they are not really fungible. If you have, for example, a straddle position, you would only have theta v, or mostly will have theta v in it. And if you have a box position, then you are going to have only theta c. And you really cannot hedge your theta exposure in straddle with the box. That doesn't make sense. That's why it is important to report them separately and risk manage them separately. Now let's talk about the practical aspects of calculating those Greeks. Obviously, one way is to calculate them by bumping, but in practice, this is going to create a lot of problems if you have periods of time when either time v or time c do not tick. Just like, for example, time c doesn't tick intraday, or time v may not tick overnight when the market is closed. Some people may prefer this definition of volatility time. But also this will create problems around dividends. This will create problems right before earnings if you put earnings variance into volatility time. So this creates a lot of numerical and other practical problems. A better way to calculate thetas is to go back to the Black-Scholes PDE. If you look at it, you will see that it gives you the relationship between different Greeks. The first term is your theta, and the second is gamma and delta, and the present value of the option. So you can express theta through Black-Scholes PDE in terms of other Greeks. Once you do this, you can clearly see that the first term that has gamma in it, that's your theta v, and the other two terms correspond to theta c. Defining theta v and theta c in this way is a considerable improvement on top of the textbook theta, both in terms of understanding your risk and also useful in P&L attribution. However, they have several problems. Notice that these are still infinitesimal derivatives. One consequence of this is that for very short-dated options close to expiry, if your underlier is close to strike, the theta is going to explode, theta v specifically is going to explode, and it's not really a meaningful number that you can aggregate with thetas in other expiries. There are certain ways how you can address this problem, for example, by capping the absolute value of theta by the time value of the option divided by time to expiry. And that's what's usually done. But still, the infinitesimal theta may not be exactly what traders want to see. The other theta that traders often care about is scenario theta, when you shift time forward by 1 day and do evaluation of your position. So as we said, theta is when time changes and nothing else changes, but what doesn't change? It's actually not a simple question. When we change the as of time of the valuation, you need to make several decisions. For example, does your underlying price stay the same, or do all your forwards stay the same? Then when you are shifting the volatility surface, you can make different assumptions about the time dynamics of your volatility surface. Of course, you can do sticky strike, and this is commonly done, but that's very unrealistic and causes a lot of practical problems. So how does the volatility surface change when you change the as-of time? There are several choices that you may have. Does your spot stay the same, or do your forwards stay the same? That's one assumption that you need to make. The other one, what happens to the term structure of your at-the-money vol? The simplest assumption could be that the term structure of your at-the-money vol stays the same as a function of time. In this, one interpretation of this would be that if the term structure of your implied volatility is mostly determined by the term structure of your risk premium, then even if your expectation of the future realized volatility is roughly flat, but the shape of the contango in the vol curve is mostly explained by the term structure of the risk premium. In this case, as time shifts, the functional form of the contango will stay the same as a function of time. However, if you want to think of your shift more in the Q measure rather than P measure, then it's sensible to shift the at-the-money vols in such a way that your forward starting variances remain the same. When it comes to shape, a good assumption would be to assume that the shape of the curve stays the same as a function of tenor. And that's what implemented in Vola Dynamics. These are the choices you have in Vola Dynamics when you calculate 1D theta. This concludes my presentation about the most important Greek in derivatives trading. I hope you enjoyed it, and I hope you learned something that's not available in the textbook. And if you have any questions, you're always free to reach us at Vola Dynamics. Hope this was helpful.